Alright guys, so this will be my third video in the playlist on abstract algebra, and this video I'll be talking about some sets which have binary operations which are not groups and why. So I guess one of the really nice examples are the set of irrational numbers. And by the way, this symbol with a colon and an equal sign, that just means defined as. There are lots of ways you can write defined as, but that's the one I like, so that's the one I'm going to be using. So the irrational, let's consider them. So they are defined as the set of reals which are not rational. Of course, you have to have 0, because when you delete the rationals, you also delete 0. So you have to put it back. And under multiplication. So are the irrationals a group under multiplication? And there's actually one very quick way to check to see if they're not. Consider square root of n times square root of n. Yeah, let's consider that case. So what happens when n is not a perfect square? So if we have something like, square root of 7 times square root of 5. Actually, no. What am I doing? Square root of 7 times square root of 7 has to be the same integer. So what happens when this? What goes on when we have this? Well, of course, we know that this is just simply equal to 7. Now, what went wrong there? Why is this not a group? Because if we have square root of 7, square root of 7 is irrational. We know that from lots of different ways. Every non-perfect square is irrational. So we square root of 7 times square root of 7. These are indeed both irrational. So they do both come from the set. So we do have a times b are irrational. I'm just going to put I for irrational. So that's true, but it's equal to 7, and 7 is not irrational, so it fails the closure property. Because 7 is rational, 7 is not a member of the irrationals. So so essentially it's not closed under multiplication, and because it's not closed under multiplication, we don't even need to check the other ones. It's just not a group, and that's usually a good way to check. If it's not closed, then we know it's not a group, and that's a very nice way to check that. Really, if any axiom fails, then it's not a group. But closure is one that fails, I guess, maybe a little bit more often than the other ones. So that's one example. Now, what about the integers under multiplication? Now, this looks a little weird because the integers under addition are indeed a group, and I think I've maybe shown that already. But under multiplication, they're not. And so I'm just going to go skip right to the step where I show that they are not a group. So consider we have something like 4. 4 times 1 over 4, and this of course is going to give us 1. Because remember, we said that for the integers, the multiplicative identity, or e, so a times 1 has to equal a, and of course we know that 4 times 1 is equal to 4, but we also have to have inverses. So we have that a times a inverse is equal to 1. So essentially we need to have 4 times a is equal to 1, and a has to be an integer in order for every element to have an inverse, or at least for 4 to have an inverse. So for 4 times a, but what is that inverse? We know it's 1 over 4, but 1 over 4 is not an integer, and since it's not an integer, we know that not every element has an inverse, and so that is where the integers fail to be a group under multiplication. All the other axioms are satisfied. It is closed. If you have a times b, it always is equal to c, and c is indeed an integer. But this property where every element has inverse fails, and so it's not a group. And so actually, there's a special name for this. When not every element has an inverse, but the other properties are satisfied, we call that a monoid. So monoid, basically, it has closure, it's associative, and it has an identity element. Those 3 properties are there for monoids, but not every element has an inverse. So that's what makes it different from a group. And so that's why integers under multiplication are not a group. And so I guess that's pretty much all. It's important to, oh yeah, one other thing to note. In order to prove that something is a group, you have to make sure that all the axioms are satisfied all the time. I did mention that, but also, if you find just one counterexample, then you know it's not a group automatically. It's important to know that if you find a counterexample, then you are done with your proof. But in order to prove something is a group, you do have to prove it for all cases, not just for some cases. Like I couldn't just simply say, have said square root of 3 times square root of 3 equals 3, and then it would be done. No, that wouldn't be sufficient. It would have actually, I take it back, that actually would be sufficient because one element does not follow property. So actually that would have been sufficient. I misspoke. So backtracking what I was saying, if you have one element from this set and another element, because you can have A times B, where you can have B is equal to A. So you have A times A, or A operation A is not a member of the set, then you're done. So if even just one element fails to have the group properties, then you're also done. So that's important to note when showing something is a group or not a group. Just check all your axioms. If even one element fails, or say two elements fail, then you are done with your proof. And so that's all I have to say for this video. I hope you guys enjoy, and I'll see you guys in the next one.